Okay, this is the Zoom meeting for calculus for Friday, October 23rd. Just start off with some random problems. Why don't we try, we're doing 9.3 and 9.4 this week, so 9.3, page 613, problem 17. Summation n equals 1 to infinity of 1 over 2n plus, we have a participant. Cubed. Do you have any, we're back to one participant. Okay. Maybe you're trying to log in. Go ahead and keep trying. I don't know if you can hear me or not. Let's see. We're going to test for convergence or divergence with the integral test. So for the integral test, we take the integral of 1 over 2n plus 3 cubed, the n 1 to infinity. I'm supposed to use x, but get sloppy. Oh, there's a 2n plus 3 cubed there. So we'll have u is 2n plus 3. du is 2 dn. So we will take integral 1 to infinity. I'll write it out in the end for one more step. 1 over 2n plus 3 to n plus 3 cubed dn, and we'll make it 2 dn. And we'll put a 1/2 to fix it. That will make a 1/2. I'll drop the 1 infinity because I'm going to u. 1 over u cubed and du. Now that's a u to the negative 3. So there's a 1/2 integral u to the negative 3 du. Which is making 1/2 u to the negative 2 divided by negative 2. I'll make that a negative 1/4. Negative, and then 2 times 2, 4 on bottom there, and 1 over u squared. And that back down. So I'll make negative 1/4, 1 over, I think my son just logged on. So I'm going to have to redo the camera. Pause for station identification. All right, see if we can get the camera back. Oh, seems like we got 2 participants now. Can you all hear me?
Yeah, I can hear you.
Okay. Let me go ahead and finish this problem, then we'll check and see if y'all got any questions you want. I'm almost finished with this one. I was just starting with problem 17 on 9.3, just worked a random problem. So it's 1 over 2n plus 3 squared, and you're putting in 1 and infinity. And so you get a negative 1/4, 1 over 2 times infinity, add 3 squared, minus a negative 1/4, 1 over 2 times 1, add 3 squared. And this is going to go to 0. All the 2 times infinity, add 3, and then you square off page. You're going to get 0, in effect 1 over infinity. So you're going to get a positive 1/4, and I believe a 1 over 25. 2 plus 3 is 5, squared is 25. So that's 1 over 100. All right, so since that's finite result, so I can make my conclusion, sum of n equals 1 to infinity, 2n plus 3 cubed converges by the integral test. All right, so I just picked a random one and worked it problem 17, hoping somebody would come, and a couple of y'all are here. Y'all have anything you want to see? Can't see y'all's names. I'm on the camera. It just shows me I've got 2 other people here.
Can we just see like 9.4? Start that.
Absolutely. Which one in particular?
Just like the introduction to the lesson, you know.
Okay. 9.4. We're just going to cover what's called the limit comparison test. We very cleverly abbreviate this LCT. And what you do, you're again testing for convergence. The gibberish is shown on page 618. And so what happens is you kind of do it from the conclusion back. They didn't really start with this, but you got 2 series. And you're really comparing one to the other. Well, it turns out if you then take a limit of the terms, of the ratio of the term, the AN over the BN, and you come up some number, they're calling it L, they're saying both of they'll behave the same, either both converge or both diverge. So the trick is, I have to show you some examples. The trick is to start with your original and then get another series that you know from it that you know converges or diverges. Find this limit. I don't know, I just went unstable, so you may not be able to hear me. Okay, can y'all hear me again now?
Yeah.
Okay. So the trick is to find another series that you know converges or diverges, take the limit of this ratio, but you can get some strange results out of this. You might get a finite result here, but if you compared it to a diverging, that can mean it diverges, even though this is a finite result. I know it doesn't make any sense till you see an example. So off the homework, you have anything off the homework? I give you a whole section of these. Anyone in particular you might like to see?
Can we do number 19?
Sure. So page 620, number 19, sum of n equals 0 to infinity, square root of n squared plus 1. Okay. Note that the book called them AN and BN. They're just generic names. It doesn't matter. The book is calling them AN and BN. You don't have to pay attention to that. They're just generic names. So what happens is you're testing this. Your new series comes from letting n go to infinity in this original. So what you want to do is you want to take, kind of in your head here, 1 over the square root of n squared plus 1, and let the n go to infinity. But don't put in infinity. Just imagine, all right, this gets very large, infinity squared. Well, it's going to swamp the 1. So that's going to go to 1 over the square root of n squared. N squared with n infinity will be much, much bigger than 1. So it's going to look like this. And then a square root of n squared is n, 1 over n. So when n goes to infinity, these terms are going to look like this. And you really have a sum of them. So it's going to be this is what you're going to compare to. It's very important that you know what happens with this. Do you recognize that this diverges? And usually you're supposed to give an argument. You can say it's a P series with P equal 1. You can also say it's harmonic. First power, we gave it the name harmonic. It's a harmonic series, and it diverges. All right, the point being, these terms act like this within large. Pause for station identification before we actually do the test. Any questions about this?
I don't think so.
Okay, the actual test, the LCT, the limit comparison test, takes the limit as n goes to infinity of the ratio of these two. Again, I don't keep track of what's the AN, what's the BN. I always take the original divided by this new thing I found. But you have to go through this process on whatever they give you. So that's how it sets. This is my AN over my BN. All right, so with two fractions, the next step, I'm going to divide the fractions by taking the top, multiplying by the bottom, flip of the bottom. So that's going to be a limit as n goes to infinity of n over square root of n squared plus 1. Right. Tough to work this out. I might go ahead and just put a big square root around the whole thing. You see how I can write it like this? I can put the root around the whole thing if I make that an n squared. So square root of n squared gives me my n back, and then I have my square root of my bottom. Okay, so then you can take the square root out of the whole thing and do the limit just inside. And you see how you have a L'Hopital condition? You got an infinity over infinity here. So you can do your derivative at top, derivative at the bottom. That's L'Hopital's rule. We're using L'Hopital's rule. Remember, very first back, meaning I can do a derivative on the top, a derivative on the bottom. And you see how I get a 2n and a 2n. Derivative here is 2n, derivative there is 2n. So they're identical derivatives, therefore they cancel. I get a square root of 1, which is just 1. But here's where it gets tricky. Any questions about getting that far?
No, sir.
Okay, now see, this is where it gets tricky. That's finite. You're used to finite things converging. But the problem is you compared it to a diverging. And the limit comparison test, when you read that gibberish in the box, says they behave this, they either both converge or both diverge. So the conclusion is this diverges by the LCT. Because basically the terms act like this, which diverges. Therefore, this has got to diverge. I know this gets very technical, and online is probably not the best format for this. That's why we love Chapter 9. So this is a case of getting a finite result, but it actually means things diverge. Happens at a couple places in Chapter 9. Finite results actually mean you diverge. Anybody want to ask anything more about this, or have you got another one? Want to see another one?
Can we do one from like 27 to 33, doing all the different tests?
Sure. You got one picked out you want to see?
We could do 29.
29. Okay, yeah, they give you kind of a summary of, and we haven't done every single one of these tests, just to show you. We have done, if you want to mark the ones we've done, I've shown you nth term and piece series, integral test, and limit comparison. So we've done every one in the first column. I've also showed you geometric, but I have not done a telescoping or a direct comparison. I'm probably going to leave those off. Okay, you can use multiple tests on these things. If it was just the 1/5 to the n, I'd use a geometric. But with that +1, it's not a geometric directly. This is kind of crying out for LCT. I'm not really telling you what test to use. This is crying out or LCT. See, I have very sensitive. Can y'all hear it crying out? LCT, LCT. See, I can hear that. But that means I have very sensitive ears. Okay, so what happens is if you let n go to infinity, you will have 1/5 to the n plus 1 become 1/5 to the n, which you can write as 1/5 raised to the n and put a sum. It's acting like this. Do you recognize this as geometric? The r is 1/5. That's less than 1. That means it converges. So I'm going to compare this to this. Questions about that? So on my LCT, I'm going to take a limit as n goes to infinity of 1/5 to the n plus 1 over 1/5 to the n. Any questions about this? All right, so again, I'm going to divide the fractions. 1/5 to the n plus 1 times 5 to the n over 1. The limit n goes to infinity. I'll just collect it 5 to the n over 5 to the n plus 1. And do you see an infinity over infinity situation? I'm going to use L'Hopital's rule. We pause for station identification. Losing anybody? Anybody want to ask about anything further up? I've got 3 participants now. All right, we ready to use L'Hopital's rule?
I think so.
All right, you remember how to do a derivative when your base is not, remember a derivative on E is straight E. I'm sorry, God, I read it all wrong. A derivative of e to the x equals e to the x. Remember how to do a 5 to the x? You get a 5 to the x, but you need something else. Do you remember what it was? Has it been flushed from Calc 1? You multiply by the log of the base, log 5. Everybody remember that? Is that been flushed?
I forgot about it.
Okay. Well, hopefully this reminds you. Yeah, we got any other number, you repeat, and then log of the base. Now, if this is anything other than x, you have a chain rule to them too. You see up here, you could do a log e. But what is log e? It's always 1. So they never write a log e when you do e. Okay, so when the point being, when I do a limit as n goes to infinity and I do the top derivative, I get 5 to the n and a log 5. And I get the same thing down here, a 5 to the n and a log 5. 1 goes away, of course, it's number. These are identical. So I get 1. And now I look back and I compared it to a converging geometric. So getting 1 on this problem means this converges by the LCT. Because these terms look like a converging geometric at large n. So this converges, therefore this will converge. If you think this is complicated, in the regular class, I throw the DCT at. That's a direct comparison test. That one's nasty. I'll leave that one off, but don't thank me all at once for leaving off the direct comparison test. I don't want my email box to get slammed with emails of gratitude for leaving off the direct comparison test.
I'll try not to send too many.
Very good. You want to see anything others? Any other questions about this, or do you want to see any others? You want to see something like 31? (31) is kind of crying out for nth term. When you see 2 polynomials, that's kind of crying out for the nth term. Anybody want to see an example of that?
Yeah, can we work on that?
Okay. Summation 2n over 3n minus 2. This really excels on ratios of polynomials. And you just simply take a limit. I didn't need a line. Goes to infinity of 2n over 3n minus 2, which again is infinity over infinity. So if you use L'Hopital's rule, you have the limit as n goes to infinity, and your top derivative is 2, and your bottom derivative is 3. There's no n's to plug in, so you're getting 2/3. I don't know if you remember, the point of the nth term test is this is not equal to 0. So you diverge by the nth term test. Now, this is all gibberish. What this means is when you add these up at infinity, your terms look like 2/3, because in effect your 2 is getting too small and your n's are canceling. So in effect, you're adding 2/3 plus 2/3 plus 2/3. You know, you have a whole bunch in front, but at the end, when your n's are going to infinity, you are adding 2/3 forever, which means you're just getting bigger and bigger and bigger and diverging. So the point being that if you come up with a straight limit and get something not 0, you are adding that non-zero number forever and just getting bigger and bigger and bigger and diverging. But remember, if you take a limit on your terms and get 0, it does not mean you converge. Case in point is that harmonic 1 over n. You take a limit as n goes to infinity of my 1 over n, you get 1 over infinity, which is 0, but this diverges. It's a p series with p equal 1. P series, it's harmonic, and p equals 1. It diverges because these terms do not go to 0 strong enough to diverge. And we saw that in 8.8 with that integral test. You can see it from 1 over n dn. You get a log of n, 1 to infinity, and you get log of infinity. So you don't get a finite area. We saw that in 8.8. And when you pick the terms off and sum them, it doesn't converge, even though the terms themselves do go to 0. They don't go to 0 strong enough to converge. But if you definitely get a non-zero result, you can conclude divergence. Any of this making any sense at all, or is it all just kind of like complete gibberish? Why did I sign up for this class?
I understand.
Well, we have one. Anybody else want to say anything?
I'm good with it.
Okay. Yeah, we got one more section next week. Two more sections, I'm sorry. 2 more sections, 1 more week of these tests, 9.5 and 9.6. And then we're through with tests. And then 9.7 through 9.10, a couple of sections pretty easy, a couple of sections pretty tough in those last 4 sections. Anybody want to see any more of these problems?
Can we do an integral test and a p-series test?
Sure. That's back to 9.3, right? Yeah. Anyone in particular?
I don't have a particular one.
Well, I just did 17 at the first. I want something like 19 or 21 or for an integral test.
Can we do 19?
19, got it. Nine, 3, 19. After you do more of these, you kind of figure out which, if anybody's wondering, well, gee, it is a ratio of polynomials. Why not do a nth term test like we just did? But can you tell you're going to get 0? If I did a straight limit on this, I'm going to get 0. I don't know if you can tell because the 1's going to go away, n over n squared. You're going to wind up with something over n. Put in n as infinity, and you're going to get 0. See, that's no conclusion. Your terms are going to 0, but that tells you nothing. It really only, your ratio polynomial, really only, if that's an n squared, I would do the nth term test. All right. You do an integral test if you recognize you can do an antiderivative on this. And you see how you got an n squared here, do a derivative to get an n. So that's kind of like a u du integral. So that's why it's crying out for integral test. Or integral test. So on the integral test, I do an integral 1 to infinity. Again, you just pick those limits off that sum. 4n over 2n squared plus 1 dn. Again, I'm supposed to be using x. But like I say, doesn't bother me if it doesn't bother you. All right, and you see how you could set u equal to your bottom. Keep wanting to freeze. There we are. Your du is 4n dn. Okay, I just went unstable. I don't know if y'all can hear me. So this one's easy enough. You don't even need a fix. You've got your u on bottom. You've also got your du. 4n dn, direct match, if you remember how these work. So we're going to wind up with an integral of 1 over u. This is your u. I'll write it 1 over u and then du. It'll catch up. There you are. We losing anybody? Bottom's my u, all of that is my du. I dropped the 1 in infinity because that was n numbers and not u numbers. Just keeps wanting to freeze. Okay. So I get a straight log of u. I'll put the line, but I put in the 1 infinity then. That's a log. The u is 2n squared add 1. And now I'll bring back the 1 in infinity. So I'll get a log 2 infinity squared add 1 minus log 2 times 1 squared add 1. And you can tell 2 infinity squared add, we're going to get log of infinity there. Minus a log of 3, I believe. 2 plus 1 is 3. Which means the log of infinity, which is infinity. And the integral test is really straightforward. You get infinite or something like that. This diverges by the integral test. And yeah, if you get a finite, it would converge. This one's, the integral test is really straightforward if you can do your antiderivative. Finite result, you converge. Infinite result, you diverge. Basically, you could have done a limit. In effect, I did a limit comparison for you in my head. This looks like something over n, and that diverges. Something over a first power is going to diverge. You could have done a limit comparison test on it. Would have worked as well. Questions about that? You mentioned P-series. Did you want to see a P-series test? Those are really straightforward.
Yeah, can we do one of those? Can we do 36?
Sure, 36. Let's see. I'm gonna have to find a formula for it. Thirty-six is this off page 613. Plus 1 over third root of 4 plus 1 over third root of 9 plus 1 over third root of 25. Looks to me, see how these are squares? That's a third root of 2 squared, a third root of 3 squared, a third root of, I'm sorry, I lost a third root of 16. 1 over, yeah, so 1/16. So that's a third root of 4 squared, third root of 5 squared. This is probably there's a third root of 1 squared there, if you want to see it completely. Looks like it's going to go 1 over third root of n squared. You can kind of imagine it back. Third root of 1 squared there to start off, third root of 2 squared, third root of 1 over third root of 3 squared, 1 over third root of 4 squared. Yeah, n equals 1 to infinity. Everybody see how I came up with this?
Yes, sir.
Okay. Well, then your basic algebra, third root is something squared. That's going to be a sum of 1 to infinity, 1 over n to a 2/3 power. Okay, so they call it a P-series test, but it's really straightforward. All you really got to say, this is a P-series. P-series. P is this power, so P is 2/3. That's less than 1. So it diverges. So it diverges. P less than or equal to 1. P equals 1, it's harmonic, 1 over n, and anything less than that. Notice the terms go to 0. If I let infinity, 1 over infinity to a 2/3 is 0, but it's not a strong 0. It's too large to converge. So it's got to be bigger. It only converges, P is strictly greater than 1, which is why they give you 37, 1.03, just barely bigger than 1. But you can instantly, that's a P series, and the P is greater, 1.03 is greater than 1. This 37 converges, even though it's barely bigger than 1. Questions about this? I can write that down. I don't know if you need to see it written down. 37, page 613. You have a sum of n equals 1 to infinity of 1 over n to a 1.03. P equals 1.03 is greater than 1. This converges. The P series test. Questions about this?
So for the P-series test, in the numerator, does it always have to be 1 in order to do the P-series test?
No,
like, for example, on 34, there's a 3 on top of it.
No, it doesn't.
Does that change anything?
No, it doesn't change a thing because you can pull the 3 out front. All right, so you got in 34, sum of n equals 1 to infinity of a 3 over n to a 5/3. So you could write that as 3 sum of n equals 1 to, it's like factoring out the 3. See, if you wrote this out, you'd have
Okay.
3 over 1 to a 5/3 plus 3 over a 2 to a 5/3, etc. Every term's got a 3 in it. So it's like factoring out the 3,
Yeah.
1 over n to the 5/3. That's a P series. It'll catch up. P series, P equals 5/3. That's greater than 1, it converges.
Okay, that's pretty straightforward.
No, it doesn't matter. As long as the top is a straight number, you can go off the P series test. Now, if you put an n or something, then you, if it's a single n with a power, then you can kind of divide them out, figure out what's going on. But with a straight number, you can work straight off of this.
Okay.
All right, we're at 41 minutes. Anybody want to see anything else? Yep, that's the integral test in P series in 9.3, and then that limit comparison test in 9.4 for this week. I don't know if you thought this week was difficult. Next week's probably a little more difficult than this week. Coming attractions, I know that thrills you. Anybody wanting to see any more? Appreciate y'all coming out early on a Friday morning. Does that mean we can end the meeting?
I think so.
Okay, well, thank y'all for coming out. If you got any more questions, of course, shoot me an email. Happy to answer them. But we'll go ahead and end the meeting then.